Hello, Mr. Munyon here with activity 22-4, solving right triangles, finishing up our lesson on using trigonometry to solve for sides and angles. So in this lesson, you should feel comfortable with using SOHCAHTOA to solve for a side of a triangle. We're also going to add making sure that we know how to solve for an angle inside of a triangle as well. So in addition to being able to calculate angle measures using trigonometric ratios, we're just going to make sure we know how much information we need to be able to solve for every side and every angle on a triangle. All right, so on question 1, it says in a right triangle ABC with an acute angle A, you know that sine of A is square root of 3/2. Draw a possible right triangle ABC. So sine, we know, sine of an angle is opposite over hypotenuse. So it's possible that I could have an acute angle at A that has an opposite side of square root of 3 and a hypotenuse of 2. And just to be clear, square root of 3 is approximately like 1.7 something. Whoop, there we go, 1.7. So the leg of the right triangle is a little bit less than the hypotenuse there. Okay, so I've drawn one here. Determine what must be true about this. So hopefully we know that one of the ratios that we learned in special right triangles was that when we have a 30, 60, 90 triangle, the side opposite of 30 degrees could be represented by x. The side opposite of 60 degrees would be x times square root of 3, and the side opposite of 90 degrees would have been 2x. So that means if this is a 1, this would be 1 times square root of 3 for this side, and this would be 2 times 1, or 2 for this side. So this has to be a 60-degree angle based on those ratios and what we've already learned from special right triangles. So angle A has to be a 60-degree angle. And if you're not too familiar with that, don't worry, because we're going to make sure we know how to set these up algebraically and do inverse operations to solve these. So in item 1 that we just did, we were given an acute angle and asked to find the sine who's equal to that ratio. In other words, we're using an inverse function. This can be written as sine inverse of square root of 3/2 equals 60, and the inverse of sine, or sine inverse, however you want to read it. All right, so we have inverse operations for sine, cosine, and tangent, and this makes sense as inverse operations undo a trigonometric function. Just like, if you wanted to undo, a square root, you could square it, or vice versa. If I have x squared, what's the inverse of that? You could take the square root to undo it, and that way you literally get, they cancel each other out, and I'm left with, in this case, square root of x squared would be plus or minus x. So the whole point of an inverse operation is to be able to cancel out a function, and sine, cosine, and tangent are functions that we can undo using inverse operations. So just to be clear, let's say I have an equation set up that says sine of some unknown angle equals, 8/10 or 0.8. All right, so sine of an angle equals 0.8. If you want to solve for this angle, you need to do the inverse of the sine function. So you could do the sine inverse of both sides of the equation. So I could do sine inverse of sine of the angle equals sine inverse of 0.8. And that way these cancel out, and you're left with the angle equals sine inverse of 0.8. And when I type that into a calculator, it will give me a degree measurement to represent this angle. So let's try some of these in the calculator. Let's try, we have some right here. We have sine inverse of 1/2, cosine inverse of 1/2. We have all these that we can try. So if you have your phone, that's great. Most phones, you just need to make sure it's in degree mode and turn it sideways, and you'll have the option of doing the trigonometric functions. There should be a second option on your phone that will allow you to do the inverse ones. Here I'll show you on this Desmos calculator. Oops, there we go. The Desmos calculator that we have here. Main screen, if you go to functions, whoops, you already have the sine, cosine, and tangent on the main screen. But if you go to functions, you have the inverse, sine inverse, cosine inverse, and tangent inverse. So let's check this first one here that we wanted to do. Sine inverse of 1/2. All right, and notice that's inside of the parentheses there, and it gives us, we are in degree mode here. We need to make sure we recognize we're in degree mode, because if I click it, it'll put it in radian mode. We're not doing that. And I get 30 degrees. So back here, I do get sine inverse of 1/2 equals 30 degrees. Okay, so if I was doing, I guess I could check this one, my example one. Let's do sine inverse of 0.8 and see what happens, see what angle measurement I get right here. All right, so sine inverse of 0.8 gives me an angle measurement of 53.13 degrees. Okay, so take a moment and try the rest of these in your calculator, see what you get, and pause here, because when I unpause, I'm going to have the answers on here just to check and make sure you did these correctly. All right, so here you can check your answers. If you got something different on here, two things. Make sure you're using the inverse functions on these, as well as make sure you're in degree mode on your calculator. Those are the most common mistakes, is forgetting to do the inverse functions and forgetting to make sure you're in degree mode. So we're not using these functions here. You do need to make sure you're using the inverse functions to undo something, as well as make sure your calculator is in degree mode and not radian. It needs to say degrees on there and not radians. All right, so back to actually using this to solve for the sides and angles of a triangle. How do we do that? So looking at this first question here on this page number 3, it says Trisha designs a logo for one of her clients. She needs to know all the missing dimensions. So it looks as though we know we have a right triangle with 2 legs. We don't know the hypotenuse, and we don't know either of the 2 acute angles at Q or R. So Pythagorean theorem would be really easy for that first one. Plus b squared equals c squared. You could do that one. We're not going to worry about that. We're going to start with the angle measurement because that's new, how to solve for angles. So use an inverse trig function to solve for Q. So if you want to solve for Q right here, notice from this angle, I could set up a trig ratio using the opposite side and the adjacent side. So if I was going to use a trig ratio, the trig ratio that uses opposite and adjacent would be the tangent ratio. So I know for number 3 that tangent of angle Q is going to equal opposite over adjacent. If I plug in the pieces that I know tangent of angle Q, the opposite piece is 65 millimeters. And the adjacent piece is 33 millimeters. So now this is my unknown angle. I need to get rid of the tangent function to get angle Q by itself. You just need to do tan inverse of both sides. So when I do tan inverse of both sides, on the left side, it's going to cancel out tangent and you'll be left with angle Q. On the right side, when you do tan inverse, I have tan inverse of 65 over 33, and this is what you can type in your calculator in degree mode to get the answer. So let's do that. Tan inverse of 65 over 33. So tan inverse over 33. All right, and it tells us that the angle measure is going to equal 63.08 degrees. So I get angle Q. Okay, so angle Q equals, we rounded, so 63.08 degrees. Okay. Now it says describe two ways to find the measure of angle R without finding the length of the hypotenuse. Find the angle measure using both methods. So basically, we're going to check and see which of these is more accurate, or if they give us the same answer, or what are these two ways. So at this point, I've solved for angle Q. I should be able to just use the triangle sum theorem. If I know it has to add up to 180 degrees for the whole triangle, 180 minus 90 degrees for S, minus 63.08 degrees, I should get 26.92 degrees for angle R using the triangle sum theorem. So using triangle sum theorem, 26.92. All right. Another way I could do this would be if I was to set this up the same way I solved for angle Q, and from angle R, use the opposite and adjacent legs to set up a tangent ratio and solve. So notice here, from angle R, this is the opposite piece, 33, and 65 is the adjacent leg. So I could set up a tangent ratio to help me solve for angle R. I know tangent of angle R equals opposite is 33 over adjacent 65. Do tan inverse on both sides. Angle R equals tan inverse of 33 over 65. So notice this is not quite the same as what we did before. It's the other way because we use the other angle. So let's check and see what angle measurement we get. Tan inverse of 33 over 65. Looks like we get 26.916, so that 6 rounds up to a 92, so 26.92. That's exactly what we thought we were going to get, 26.92. All right, so either way, using triangle sum theorem, or if we were to use inverse tangent function to solve for that one, we get the same angle measurement. So it says describe two ways to find the length of the hypotenuse. We already described one way. You could just use Pythagorean theorem. A squared plus b squared equals c squared. So the other way that we could do this is using trigonometry. So let's say I wanted to solve this using trigonometry. I'm going to erase some of these things we have here. And let's call QR, let's just call this X for now, just so we could solve for it. Let's say I wanted to solve for X. I could use either the adjacent leg and the hypotenuse from angle Q, or angle Q, I could use the opposite leg and the hypotenuse. Either way, I just pick one of the two legs that I know and the hypotenuse. So either sine or cosine would work from angle Q to be able to solve for QR. So if I set up sine of angle Q equals opposite over hypotenuse and plug in sine of 63.08 equals opposite would be 65 over hypotenuse x. Multiply both sides by x, divide both sides by sine of 63, and you end up getting x equals 65 over sine of 63.08 degrees. Okay, let's plug that in our calculator and see what we get. 65 over sine of 63.08. So 65 divided by sine of 63.08 and it is in degree mode. I get 72.899 or 72.90 as the length. So if I did this Pythagorean theorem, square root of 33 squared plus 65 squared, I should get the exact same answer. So square root of 33 squared plus 65 squared, 72.897, so rounded to 72.90, the exact same answer. Alright, so luckily this is convenient because in most of these, if we do trigonometry once, we are actually able to solve for the other sides or angles using more than one method. So whichever one we're more comfortable with, we're able to use. Alright, one good example there. Let's move on to check your understanding. Number 6 and 7, you could stop here and pause and see if you did them correctly, but I'll just go ahead and talk about them now. What is the minimal amount of information needed to be able to solve for all the other sides and angles on a right triangle? Well, if you have a right triangle, you need to know at least one side. From there, you also need at least one more side or an angle. So you definitely need to know at least one side for sure. From there, your second piece of information could either be another side or it could be one of the two acute angles. Either one of those would be good enough to be able to solve for all the rest of the triangle using trigonometry, triangle sum theorem, and Pythagorean theorem if you need it. For number 7, it says explain the difference between the two expressions, sine of 15 degrees and sine inverse of 0.2558. One allows you to solve for a side of a triangle in relation to a 15-degree angle. It's relating the opposite. It's the ratio of the opposite and hypotenuse sides. This allows you to solve for an angle given that the ratio of the opposite and hypotenuse sides is 0.2558. So this will allow you to find the ratio between two sides, and this will allow you to solve for an angle given a ratio. How are they related? Obviously, they're both trigonometric functions and inverse functions that you would use on solving for right triangles. All right, now time for the lesson practice. I would like you guys to try some of these on your own. Like 8, you just type them in the calculator to solve. You do one step, like right here you do cosine inverse of both sides, so you get x equals cosine inverse of 0.59. And you type that in your calculator and see what you get. You get some angle measurement, make sure it's in degrees, and you put your answer to the nearest 10th. And then the other ones is just practice solving. I'm definitely going to go over C for you guys. The other ones I'm just going to put the answers on here. So pause now, please. Alright, so here's the answers for 8. Once again, make sure you're correctly using the inverse operations. It's in degree mode to get these answers and that you rounded correctly. On 9, I did mention I was going to go over C, so let's go ahead and go over that one. So on C, we should be able to just do Pythagorean theorem to find the hypotenuse. A squared is 15 squared plus B squared is 9 squared, so 215 plus 81 gives us 306. Take the square root of both sides, we get that ED equals approximately 306 square root. You type that in your calculator, you get about 17.5, and that answer does make sense because it is the hypotenuse. It should be the longest side there. It is within reason for those. From here, if you wanted to solve for angle E, let's say you wanted to use the tangent ratio from angle E right here. The tangent ratio uses the opposite, which is given, and the adjacent. So technically we have solved for ED. We could use sine, which uses the hypotenuse, or cosine, which uses the hypotenuse. But if I miscalculated, or in this case I rounded on this one, we might not get as accurate as an answer. So I'm going to go ahead and use tangent because the opposite piece was given as 9 and the adjacent piece was given as 15. So I know that tangent of angle E equals opposite over adjacent, so 9 over 15. Do the tan inverse to cancel out. I get angle E equals tangent inverse of 9 over 15, and I can type this in my calculator like I did for question 8, A through F. So plug that in your calculator and you do end up getting 30.96. If we round to the nearest tenth, it actually rounds up to 31.0. So angle E is approximately equal to 31.0 degrees. And then we can use triangle sum. We get 59 degrees for angle D. Just 180 minus 90 minus 31 gives us 59 degrees for angle D. All right, for the last two questions here, without using a calculator, explain how to find the value of tan inverse of 1. So that means the opposite and adjacent values are the same. So if you get any value, it doesn't matter what the opposite and adjacent pieces are here. For it to equal 1, they have to be the same thing, which means your two legs have to be congruent values. So it has to be an isosceles triangle, which means an isosceles right triangle, which means the angle has to be 45 degrees. Because let's say we have, let's call this angle A. If I wanted to do tan inverse of 1, that means the tangent of that angle equals 1, which means the opposite over adjacent equals 1. Whatever value you have here, you have to have the exact same value, so that when you do tangent of A equals 1, the angle measure is going to be 45 degrees. All right. Number 11 says consider a rhombus ABCD where AC equals 8. So ABCD, AC equals 8. BD equals 12. What are the measures of the sides? So that means if each one of these is bisected here, because it's a parallelogram, that means this would be 6 and 4. So all of these are right triangles. So 36 plus 16, 40, 52. Do Pythagorean theorem, you get each side is square root of 52, or about 7.1 for each side. So because it's a rhombus, each side is bisected, or excuse me, each diagonal is bisected. So that means half of 12 is 6, half of 8 is 4. So your two legs on your right, each of those congruent right triangles is going to be 6 and 4, and then you can just do Pythagorean theorem. For the angle measurements, you just need to do tangent inverse to figure some of these out here, so I guess we can do that real quick. Let's say I wanted to solve for this one, and let's call that angle BCA equals opposite over adjacent, so 6 over 4. So angle BCA equals tan inverse 6 over 4, so tan inverse of 6 over 4, tan inverse over 4, 56.3 degrees. So 56.3 degrees, and using triangle sum, the other one would equal 35.7 degrees for those last two. So the other angles would equal 56.3 degrees and 33.7 degrees. All right. I'm going to go ahead and do a little bit more. If you're done with it, you can exit right now. I'm going to do another problem where you guys just have to solve given two sides of a triangle. See if you can solve for the other sides and angles. So let's go ahead and do that now. All right, so let's just make up a triangle with one side, with a couple of sides here, and see if we can figure out the rest of it. So let's say I have a side of 10 and a side of 7. Let's call this triangle A, B, C. I want you to figure out everything else about this triangle. So the first part should be easy. You could do Pythagorean theorem to solve for that last side. So square root of 10 squared plus 7 squared. That's just Pythagorean theorem. So square root 149. I think that's going to be about 12.1 approximately. So approximately 12.1. Okay. So let's say approximately 12.1. From here, if you want to solve for an angle, let's say I want to solve for this angle right here, you're going to need to use an inverse trig function, and you need to find two sides that you do know to help you solve for your unknown angle. So the sides that I know for sure are correct are the given ones, and from my angle B, this is the opposite side and the adjacent side. So the tangent ratio is which piece uses opposite and adjacent. So I could set up tangent of an angle, angle B, equals opposite over adjacent, and then plug in. To solve for angle B, you need to undo tangent, so do tan inverse of both sides. And now I just need to type in my calculator, tan inverse of 10 over 7. 10 over 7. And I get 55.007, so 55 exactly pretty much. If we round to the nearest 10, 55.0. So that means this angle up here has to equal 180 minus 90 minus 55 gives me 35 degrees. I guess I should have put the 0.0 on this one as well. Hopefully that helps you to figure these out. If you were given one of the angles already, then you can just use triangle sum to solve for the other one. But if you're only given two sides and you need to use an inverse trig function to solve for one of the angles, always use the two sides that you're given, not one that you calculated, because if you miscalculated or you rounded too much, your answer won't be as accurate. All right. See you guys next time.